I know I've only been doing YouTube for about a year-ish, but within that year, within the videos that I've produced, I found one thing that kind of grinds my gears. It upsets me, and that is, well, you see, YouTube has a bunch of analytics that it will give you about your channel, and one of the pieces included in that is a link to trending videos that are similar to the videos that you produce. Right? I make science content, specifically physics content, so you would expect physics YouTubers, science YouTuber videos. And while it shows some of those as like recommendations for, oh, this is what's trending, this is what people are into, 90% of what I see on that list is sloppy pseudoscience or just sloppy science communication videos in general, videos that are designed to kind of build off of the idea that, oh, people are hiding things from you, very conspiracy theory based. And I've decided, well, I am working on a PhD in physics, and someone has to start addressing these sorts of videos. And I mean, some of them are flat Earth based, but there's a lot of other stuff, and I think I can use some of my knowledge to maybe address this sort of thing. I won't lie. This is kind of not fully motivated by, but definitely inspired by watching some Mini Minuteman videos lately. He does a very good job of addressing, particularly pseudoscientific, conspiracy theory based archaeological stuff. And while physics doesn't have the same type of environment, there's definitely that sort of content out there. Now, to begin this sort of examination, I wanted to look at this video that was produced by someone who left a comment on one of my videos. See, I did an interview with a grad student whose research is related to a dark matter search at CERN. Now let me outline quickly what we think dark matter is. We don't know what dark matter might be. We've got a few properties. We don't even know if it exists. But based on what we've seen, we believe it probably exists, and if it does exist, it could be a myriad of different things. And so within the physics community, we go looking for each of those different potential things that dark matter could be and hope that we find a signal. And if we find a signal, then yay, we could maybe figure out dark matter is X or Y or Z. Or of course, if some of our theories around dark matter isn't come true, then that is also an X, Y, Z. Dark matter is not that. Very simple, very important sort of stuff that we look for in physics. I mean, it's a general thing that we do for more than just dark matter, but for the sake of this, I got a very long comment, 2 comments, about essentially saying everything that's been kind of being covered in this video is bunk. Dark matter doesn't exist. It is, what was it? Dilated mass. And so I was interested by that comment, and I went looking into if there were any theories about dilated mass. Now, as a scientist and physicist, I don't believe that it's a good idea to be very definite about some things that we aren't positive on. We don't have positive data exactly saying X is true. Like even when it comes to dark matter, we believe dark matter exists. Could it not exist? Maybe. But you've got to, you can't just say, well, it doesn't exist because we haven't found enough proof to justify it not existing, just like we haven't found enough proof to fully say it does exist. We believe it does because we have a lot of proof pointing towards existence, but of course we have never observed it properly. Anyways, I didn't really find much, but the commenter left, the commenter didn't leave anything, but I went to the commenter's YouTube channel, and lo and behold, they've posted 4 videos, and one of their videos was about no dark matter. It's a 3-minute long video. I went and watched it, and it was not very good. So, today we are going to watch that video together, and I am going to sort of break down something that they are saying, or what I believe they're saying, because some parts don't make much sense. And we're going to do some semi-debunking, but also just addressing science YouTube videos that are, just sort of junky. I don't want to say that this is going to be a mean video towards said person. This isn't supposed to be like an attack or anything. This video is not a very good way of displaying scientific knowledge. If this is something that you believe in and that you have enough evidence for, there are better ways to be displaying this, and your current evidence that you're using is rather poor. I'm sure you're very passionate. I would assume you're very passionate based on the comment that you left. So don't stop being passionate in science and physics. But I think it's very important to address this, especially since it's had a good amount of views. Just before we get into this, I'm Owen. I'm the host of the Quantum Mic, and I am a PhD grad student doing experimental particle physics as my PhD program. I have a background in astroparticle physics, as well as some background in astrophysics, because that was what my bachelor's was in. So I have experience with regards to physics stuff. I also have experience with dark matter. 2 experiments that I have worked on, well, 1 experiment and 1 analyses for the Atlas experiment, were dark matter focused. So I have knowledge about dark matter or alternatives to dark matter to some extent. So I believe I'm fit to talk about this. If you like science, physics, are interested in learning, this is the channel for you. We cover mostly physics stuff, but we do talk about a lot of other science things. I bring on people who are experts in science and science communication to come talk about their research or their work. So if you're interested in that, I would love a little like and subscribe left in the video. But now, let's begin. Alright, well, before we begin, make sure you got your headsets on. I'm going to make sure that this video is sharing its audio. This is a video titled Dark Matter is Dilated Mass by Sean SO7. I have put myself in this upper corner because Sean is good enough to have put subtitles. This video is going to be definitely very interesting. So what you're going to see as we watch this, and I'm not going to cut anything, it's just going to essentially be, we're going to play the video, I'm going to react, we're going to play the video, we're going to react. There's going to be a text-to-speech audio, which, I'm going to be honest, Sean, not the best look for trying to make me confident in what you're saying. But that's a bit of a personal thing rather than like an actual fact. But we're just going to make our way through and watch this. So let us begin.
Dark matter has been theorized to explain the abnormally high rotation rates of stars in spiral galaxies. There must be far more mass than what is visible to explain this phenomenon. The explanation has to do with what exists at the center of galaxies. Mainstream thought today is that singularities, black holes, exist there.
Okay, we're off to a great start. We're only 28 seconds in, and there are issues. There is incorrect information, correct information. So let's just let me slide through as we cover things. All right. So dark matter has been theorized to explain the abnormally high rotation rates of stars in spiral galaxies. This is true. This is where the first sort of thoughts behind dark matter came from. Essentially, objects orbit related to the total mass in the center, as well as how far out from the center they are. When it comes to mass, if we essentially have a really big object with a lot of mass, as you move further away from it, you can kind of treat it as a pinpoint. This is also true for gravity in general, so a good simplification when it comes to gravity is any mass within the radius that you are far away from can be treated as being at the center of said radius for an estimate. So as we move out further and further and further from the galaxy, the mass within the center changes, and as that central mass changes and the radius from the center of the galaxy changes, we can approximate the rotation curve. And of course, this is at like a very basic level. If you want it to be more accurate, we can treat the distances and the gravitational impact more precisely, but this basic model essentially fits what we would expect. And what we would expect is, near the center of the galaxy, as we go out from the center, there's a lot of mass, so there's going to be things moving very quickly because they're also very tight and close to the radius. But as we move out, the velocity, rotational velocity, or the rotational period of stuff orbiting further outwards is going to slowly peak, and then it is going to sink down. Essentially, as you get further and further and further away, the masses dissipate out. This is because, okay, you look at the galaxy and you see matter. Matter interacts with light, so we see that matter by the light that is produced by the galaxy, or the light that we see scattering off of the objects. We can use that information to estimate the amount of mass within each galaxy and within each section of the galaxy. So we can essentially model, moving further and further out from the galaxy, how much mass should be in the middle. And this sort of rotation curve is what we should expect for most galaxies. Well, what we saw, instead of going up and then down like this, we found that the rotation curve kind of comes up and then it plateaus. And so what that means is, as we're moving out and out and out by the radius, there is enough mass being added in to compensate for that change in radius, meaning that the velocity stays similar. That would mean there is mass there that we don't see, based on the assumption, of course, that our model of gravity is correct, and general relativity is also correct. Well, relativity special and general relativity are correct. And in that situation, essentially, they kind of went, well, what if there is mass that we can't see? And then from that, we went, oh, there might be dark matter. Now, keep in mind, he said that it had to do with the center of the galaxy. Let's move forward. Dark matter is theorized to explain... I thought I had just hit the piece. The explanation has to do with what exists at the center of galaxies. No. The explanation for the rotation curves that is related to dark matter has to do with there being stuff outside the center of the galaxy. That is why those rotation curves vary, is because if there is mass impacting things, it has to be due to there being mass at that further radius, which is why we kind of theorize with a lot of galaxies that they have halos of dark matter, essentially big rings or circles of them, or even like spherical shapes. It all depends on the rotation curves, and I'm not an expert in the exact formations, but usually like dark matter halos, which are sort of a formation of a lot of dark matter on the edge of the galaxies, and that's what allows that rotation to remain. It does not have to do with the center, so it doesn't make a lot of sense why we're suddenly going to talk about what's in the middle of the galaxy, which is a black hole, usually. Not for all galaxies, but usually a black hole. This is where another problem comes in. So before the complete sidetrack from dark matter to black hole, which is just poor communication. I've watched the video, I know where he's technically going with this. The use of mainstream thought today, it is mainstream that black holes and singularities exist, but that's because there has been a lot of evidence put forward for them existing. They might not exist. That is still open for, consideration. But considering the fact that we have taken a picture of one and it looks like what we expect a black hole to look like, it's really hard to kind of say that they may not exist. And those spots where we think they exist, you need to have an adequate reason for them to fail to exist. And we're going to be talking a bit more about this sort of debate of black holes existing or not later in this video. But the use of mainstream thought today, while true, just the wording makes it kind of sound like those mainstream archaeologists, mainstream scientists. Like, we consider it scientific fact that black holes exist because of the amount of research that has been put into the theory behind black holes, as well as our experimental observations, right? You can have all the theory that you like, but until you have a physical experimental observation to justify your theory, it's not very helpful. And so, like, it's more than just mainstream. It is almost essentially treated as fact because we have enough stuff to support it. So if you're going to suddenly throw out that they don't exist, you need to be able to back that up. There have been attempts to say that black holes don't exist. I remember there was an article, I think this was back in the early 2010s, If I can find it, I'll put it in the description, but I haven't been able to find it yet when I've gone looking. But essentially, the idea was, oh, we've done some modeling, and the modeling says black holes can't exist. There was an issue with their model, and they kind of went, oh no, actually, they might exist. So, we are open to this fact, and if there is enough evidence to support it, theoretically as well as physically, and are able to justify for what we currently observe, then it's valid to say. And we're going to find that Sean here does not do that. All right, let's continue. So we were talking about black holes. Got this beautiful visual about our mainstream thought today. So let's see how Sean ropes black holes into explaining dark matter. All right, let's go.
Today is that singularities, black holes, exist there. Most people don't know that Einstein said that singularities are not possible. In the 1939 journal Annals of Mathematics, he wrote, "The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities." Schwarzschild was the first to raise the issue of general relativity predicting singularities do not exist in physical reality. Although the theory given here treats only clusters, star clusters, whose particles move along circular paths, it does seem to be subject to reasonable doubt that more general cases will have analogous results. The Schwarzschild singularities do not appear for the reason that matter cannot be concentrated arbitrarily, and this is due to the fact that otherwise the constituting particles would reach the velocity of light.
Okay. Where to begin here? Let's go back to the Annals of Mathematica with Einstein. So, Einstein did write this paper. This is an actual quote, minus those quotation marks where he is sort of explaining things. I believe those weren't in the paper when I read it. Gotta just move this video back to where we've got Einstein's beautiful, beautiful mustachioed face. Here we go. So yes, Einstein, I like to point out, he does not give a link to the journal. I will put a link to this journal in my video. But, well, more specifically, the paper that Einstein submitted to the journal in 1939. So Einstein did essentially submit this article, and let me find the name of the paper. I had this written down, but my handwriting's terrible. Yeah, so Einstein's article in the paper named "On a Stationary System of Spherical Symmetry Consisting of Many Gravitating Masses." He essentially does some math with regards to relativity, and then based on his calculations, he says, well, due to this, black holes can't exist. But there's a few issues. There is a paper that is published in the same article a few months later by Oppenheimer and Sidney. Yes, that Oppenheimer, the bomb guy. It's like the one paper both of them ever did on black holes. But essentially, they wrote another paper, and they were able to show that black holes could exist, and they could be formed from stars that were like 5 times the mass of our sun. Einstein is correct in his math. He is incorrect in his sort of conclusion. Essentially, what this paper is about is Einstein looking at, if I have objects orbiting a black hole, how fast do they go? Or is there sort of a reasonable shape to their orbit? And the thing is, Einstein essentially comes to the idea that, we can get particles in a stable orbit around the black hole, but to do so, they would have to be moving at the speed of light or faster. And essentially, I mean, he's not wrong in his math. He designed relativity. He was very good at doing the math related to, the system that he designed. However, his assumption that, they can't get to the speed of light, therefore the black hole doesn't exist, because, I can understand where he came from. Essentially, Einstein's concept is, the speed of light is a universal maximum. as particles accelerate closer and closer to the speed of light, unless they have no mass, they can't meet the speed of light, which means it's impossible for them to reach the speed of light, which would mean it would be impossible for the particles to start orbiting the black hole or to send towards the black hole because they will reach the speed of light. The thing is, when objects get accelerated, especially particles at a high energy, they can start to radiate said energy off as light, and that's kind of what we get nowadays. So if you've ever seen that picture of the black hole, right, you got sort of that red ring, or those red rings around it. The black hole isn't actually making the red rings. The black hole's within that central black spot, but those rings are those particles that have now been heated up. So they don't actually reach the speed of light, but the energy that's going into them heats up the particles. They exude the said energy as light as they sort of enter the orbit, but they eventually get consumed by said black hole. So it is possible. One, Einstein made a mistake here. Two, future papers have been able to actually justify the existence of a black hole, the existence of the creation of a black hole. This paper doesn't say they can't be created, outside of the fact that Einstein says you can't arbitrarily smash mass together. But again, Oppenheimer and Sydney were able to show, oh, we can smash this mass together. And so they were able to prove that it could exist. What I really don't like about Sean's use of Einstein here is twofold. Number one, you have chosen an article from 1939. That is almost 80 years ago. That is more than 80 years ago. And the fact, I mean, it is more than 80 years. It's almost, we're getting close to 90, but it isn't quite yet. But you've selected like one of the first articles on black holes. There have been hundreds of other papers and articles which have far more modern knowledge being applied to them that actually can justify why black holes can exist. If you want to use a paper to justify black holes not existing, pick a modern paper. Like I said, there was analyses done in the early 2010s. There's probably something recent too. You could find something new. But you've decided to go back to 1939. Why? Because it's Einstein. Because everyone knows Einstein is smart. Einstein can't be wrong. Einstein designed the system. And therefore, we've essentially used, well, because Einstein is Einstein, anything he says goes and would be true. And that's just bad logic. It's bad communication. It's misleading. And it's kind of offensive to just the existence of Einstein. I mean, Einstein was wrong. We know Einstein has been wrong about things. He was wrong about the cosmological constant because he added it in. I mean, okay, he was right to include it. He was wrong to think that it was wrong. He said it didn't make sense, therefore it's a mistake. He was very wrong about what he believed about quantum mechanics. So Einstein is just sort of being set up here as like well, it's Einstein. He can't possibly be wrong. And I'm a little bit offended about your use of Einstein, Sean. I'm really sorry. It's just not justifiable in any way, shape, or form. Anyways, he's going to continue to go on about this, so let's watch that piece.
He was referring to the phenomenon of dilation, sometimes called gamma or Y. Mass that is dilated is smeared through space-time relative to an outside observer. Even mass that exists at 75% light speed is partially dilated. Time dilation is just one aspect of dilation.
Okay. We're already going to break this down again. So essentially, he's referring back to Einstein's statement, which is vaguely related to dilation. That's due to the fact that essentially within relativity, within our current model of mathematics for relativity, speed of light is constant. Everything seems to say the speed of light is constant, and that means for two separate observers, the speed of light needs to always be the same. So there's some issues with that because, well, for example, let's say I am on a skateboard and I have a dart and I'm going to throw said dart. My skateboard's going at 5 kilometers an hour. I throw the dart at 10 kilometers per hour. Relative to me, that dart is going at 10 kilometers an hour. But you're standing beside me and you watch me zip past on my skateboard and throw the dart. That dart, relative to you, is actually going to be moving at 15 kilometers an hour because it's got the 10 plus the 5. So for both of us, the dart is moving, but the dart is moving at different speeds. But now if this was a light, I turn on a light, for both of us, the lights need to both be going at the speed of light, which requires some warping of distance or time relative to the observer, and that's where we get dilation and contraction. So it's like length contraction, time dilation are the two most famous ones. Essentially, the distance between objects shrinks, or the amount of time experienced for one person compared to the other increases. It dilates. It gets larger. And so when things get near the speed of light, if they have mass, said mass dilates. I've never heard gamma referred to as dilation in my experience using it, but it is a factor that represents both lengths, contraction, and time dilation. It is essentially a factor related to the velocity of the object relative to an observer in relation to the speed of light. And so as that velocity is closer to the speed of light, gamma gets infinitely large, and eventually it reaches infinity. So that's why when it comes to relative mass, which is what he's kind of talking about here, mass is another factor that dilates. So if I'm watching you go by really near the speed of light, your mass is going to you be the same, but to me it's going to look like you have gained a lot of mass. You've gained a lot of weight, and that is essentially what's going to be related to gamma. Relative mass is equal to gamma times mass. Yeah, that's true. Smeared through space-time relative to the outside observer is sort of a weird description. I've never heard of mass being used in terms of smearing. I went looking, couldn't find any sort of definition. Mass is very distinctly in its location. This isn't sort of in like a quantum probability zone where it sort of smears out. This might just be a miscommunication on his part. But, the mass will warp space-time, so it warps space-time relative to the outside observer. Maybe that's what he means, but smeared is just not the right descriptor. Of course, I'm not an expert in relativity. That is one field that, I took a course in it, and I had an interest in it when I was much younger. So, I have experience with it, but I am in no ways an expert on said topic. So perhaps I could be wrong. Yeah, he is right talking about the fact that things are dilated. Technically, things are always dilated relative to the observer. It's just going to be essentially nothing for you. That's why what's great about relativity is that it works at the high velocity to describe how things work near the speed of light, but for the everyday observer, it essentially boils down to Newton's physics, Newtonian physics, which means for you and me, we can use Newtonian physics perfectly fine relative to each other because neither of us are going near the speed of light. So yeah, the statements aren't wrong. It's just kind of weird to be talking about mass dilation because, again, we showed that Einstein was wrong in his statement. And by the way, both of those papers, I'm going to put both of them, Einstein and Oppenheimer and Sidney's ones, in the description because it's important that the people watching can have the resources if they want to learn more. One of my other issues with Sean's video, because he didn't put anything in the description with regards to articles. All right, let us continue.
General relativity does not predict singularities when you factor in dilation. Einstein is known to have repeatedly spoken about this. Nobody believed in black holes when he was alive for this reason.
Okay, we already debunked this. I don't know the specifics about Einstein's belief with regards to black holes. Likely, he probably did his calculation. Black holes were not taken super duper seriously until we had more quantitative results to justify them existing, but they were considered. And, people believed that they could exist. Again, there was multiple papers. I'm going to keep pointing to the paper by Oppenheimer and Sidney because it was in the exact same year as Einstein's paper. Also, dilation impacting things, again, we can explain this if you consider things outside of the worldview that Einstein had when he wrote his paper in 1939. There is a lot more science about this now. There has been a lot more time spent coming up with different models for singularities and black holes. And I'd like to also mention, technically a black hole doesn't necessarily need to be a singularity. It probably is, but we don't really know past the Schwarzschild radius. Essentially, there's the Schwarzschild radius is the point of no return for a black hole. A very simple way of kind of describing it is, if you consider like every planet has gravity, it has an escape velocity, essentially the velocity you need to be going at to be able to escape the gravitational pull from said planet. Well, for the Schwarzschild radius, the velocity that is needed to escape would be that of the speed of light. Essentially, it would be what distance from a point that has all said mass within it would you have to be able to escape at the speed of light. And so technically everything has a Schwarzschild radius. You, me, Einstein, everything has a Schwarzschild radius. It's just smaller than the actual radius of the body. Our sun has a Schwarzschild radius. The Schwarzschild radius of the sun, I think, is like 5 millimeters, something like that. Anyways, it is considerably smaller than the actual radius of the sun. And because of that, you would have to compress everything in the sun down past the Schwarzschild radius to turn it into a black hole. That's essentially why you, me, your cat probably can't be turned into black holes. Because even for us, our Schwarzschild radius are even considerably smaller than that of the sun. But once an object is within its Schwarzschild radius, it turns into a black hole. We don't know what happens to the mass within the center of that. Using, our understanding of relativity, it is likely all that mass would essentially pull itself into a singularity point. There's no way of really knowing. We can't look at it. Light can't escape, and if light can't escape, there's no hope of us being able to find anything out unless we have something that can travel faster than the speed of light. But if that was the situation, man, if tachyons existed, it would definitely be cool. It would make the world really weird, but, technically, maybe we could look into the black hole. Anyways, let us continue with this statement. So again, just because Einstein said doesn't mean anything. Just because this was a justification doesn't mean it works anymore, right? There used to be a theory that giraffes got their long necks because, they would essentially grow to reach the trees, which was like half-baked evolution, but not really. I forget who came up with that. Anyways, right? Just because this is something that was thought about then, it's been a long time. Things have changed. So, justifying it wasn't believed back then, well, yeah, but just because they didn't believe it back then doesn't mean that it's true. And again, you're not using modern science or physics to explain anything. All right, let's continue.
Nobody believed in black holes when he was alive for this reason. Wherever there is an astronomical quantity of mass, dilation will occur because high mass means high momentum. There is no place in the universe where mass is more concentrated than at the center of a galaxy.
Okay. Oh, no. All right, so we were talking about dilation, and now we're talking about momentum, and we're saying because there is a high quantity of mass, dilation must occur. No, now we're talking about warping of space-time. So space-time warps due to mass. That's one of the ways that we kind of describe gravity using relativity. Momentum is related to mass, but it's also related to velocity. Now, if there is velocity, there will be dilation, and that is, of course, velocity relative to an object. So too is momentum based on mass and velocity. So it would be the relative mass and the relative velocity of the object. But just because you have a lot of mass doesn't mean that you have any momentum. You could have the sun not move, and it would have no momentum. But as soon as the sun's moving, sure, it'll have a lot of momentum. That's fine. But you can also have very little mass and have it moving very, very quickly, and it will have a whack load of momentum. So this statement is just wrong. I don't quite know. He's trying to justify the center of the galaxy being not a black hole, but being a bunch of dilated mass. I went looking for a paper on this, and I found one 2-page article that looked very, very dubious. I will link it in the description. But it also was based off of very, very simplistic mathematics and vaguely said, could be a thing. Wasn't by anyone really well accredited within the physics community. So it's just, I couldn't find any foundation to kind of meet what he's going to be talking about, and I guess I'm going to loop back to this in a moment. There's no place in the universe where mass is more concentrated than the center of the galaxy. Well, yes, but that's because it's usually a black hole, which is also very, very dense, probably the densest thing in the universe, if they, again, exist, which we believe they do based on our empirical observations, as well as neutron stars, which are also incredibly dense. So, yeah. Let us continue.
It can be shown mathematically that the mass at the center of our own galaxy must be dilated. This means that there is no valid XYZ coordinate we can attribute to it. You can't point your finger at something that is smeared through space-time, or more precisely, everywhere you point is equally valid.
Okay, we're doing a lot of pausing this last little bit, but it's just, there's a lot to unpack. All right. We've shown mathematically that the mass at the center of our own galaxy must be dilated. Where? He does not show it in this video. He does not link any papers where it is shown. I could not find any papers talking about it outside of that one sketchy 2-page, I don't even know if I'd call it a paper. But there is, I can't find any justification behind a dilated mass center of the galaxy theory, right? I'm open to it. It's very important that we have a lot of different theories that could justify what exists, but we've also got to keep in mind that what our current observations are. If what he has said could justify this, which from what he has currently displayed really can't, how would it also meet? It doesn't actually explain the dark matter thing. Would it match what we see when we look at a black hole or when we look within that area? Does it match our current model? Does it match our current observations? The observations are what matter most, right? You can believe black holes exist, but if, let's say, our measurements match our current our current theoretical model for black holes, and then it's off by a factor of 2. There's an issue either with our model or there's an issue with our measurement. We would then need to double check. But, if there's an issue with our model matching our measurements, and our models are usually pretty precise nowadays, that's cool and interesting. So if you come up with a new model, if your model is even worse than our current model matching our data, there's even less of a reason to justify or meet your explanation. This just isn't well justified, Sean. I'm really sorry. You seem to be very passionate about this concept. If you're going to be presenting this, it's generally misleading with regards to the actual science and information. It seems very cherry-picked, and I can't find anything backing you up. And if you're going to say, because you're a scientist in academia and you're going to be gatekeeping, no, I'm very, very invested in citizen science and having, multiple viewpoints when we go ahead and look for things, because that is how we can check what we have observed against these new models, right? We didn't know about the photoelectric effect being what it was until Einstein came up with a theory to justify it, and we checked it, and it matched and justified it. That's why he has a Nobel Prize. It's not because of relativity, but it's because of the photoelectric effect. And that is true for so much of physics and science. This is just science slop on the internet to me. I'm really sorry. And to follow that up, I mean, you're talking about the mass being smeared through space-time where you can't point equally. You very much seem to be mixing this up with sort of vague concepts around the Big Bang. This isn't how relativity works. This isn't how dilation of mass works, at least to my understanding and my research to, check this and to check your video. And this wouldn't justify dark matter. Based on what you presented, it doesn't in any way explain the rotation curve of the galaxy, let alone we haven't even addressed the other evidence of dark matter, like gravitational lensing, that we can see with regards to it. Just the impact of invisible gravity when, like, we've watched galaxies collide. It's just... and I know I should be saving this for the end, but I kind of need to do it here because it's related to what we're currently talking about. Anyways, let us continue.
Time, or more precisely, everywhere you point, is equally valid. Galaxies with very, very low mass, or low mass in their centers, do not have enough mass in their centers to achieve relativistic velocities. Therefore, they do not contain dilated mass. To date, 5 very, very low-mass galaxies have been confirmed to show no signs of dark matter. The missing mass needed to explain the abnormally high star rotation rates in galaxies is dilated mass.
Okay. I didn't notice this until now, but there's actually like a name in the top corner over here. So let me move my face. Whoop. Nope. I moved the video. But you can see here, there is like a little label for the galaxy he's showing us. And the first few times I've watched this, I've said, you've mentioned 5, but you don't actually name them. I want to just see if this galaxy is one of the ones, NGC, dash 1277. I want to see if this is one with a black hole or without a black hole, because if his video is to be believed, these galaxies that he's showing us here with labels should be low mass galaxies that have been confirmed to have no signs of dark matter, and then also shouldn't appear to have black holes based on his justification by the fact that they don't have enough mass in their center to have relativistic speeds, and therefore don't have dilated mass, and therefore they wouldn't have the equivalent of a black hole in the center, right? Because what he's been saying so far has been, well, if it has a black hole in the center, it actually doesn't. It is just dilated mass. Well, let's see. Okay, so this galaxy does have a very unusual rotation curve, which suggests that it may have very little dark matter within it. Not no signs of dark matter, just very little signs. Now, this galaxy that he is bringing up as evidence as having no signs of dark matter appears to have potential signs of low dark matter, but it does still potentially have signs of maybe having dark matter. We don't know. It also very much seems to have a supermassive black hole. Based on my very quick lookup, the black hole, though, was initially suggested to have 1.7 times 10 to the 10 solar masses. Not as massive as they once thought, but still a black hole. So there still seems to be a black hole at the center of this galaxy based on our observations. Based on what has been presented here by Sean, it has a black hole, but the black hole won't actually be a black hole. It will be relativistic mass, and therefore, because of the dilation, we will have dark matter somehow. Don't know, don't care. The justification, either way, based on Sean's logic, there should have been no sign of a black hole, but we have signs of a black hole here. Sorry, Sean, that doesn't make a lot of sense. Let's tick back. But here, yeah, galaxies with very, very low mass don't have enough mass in their center to achieve relativistic velocities. They do not contain dilated mass. There is a way to potentially explain this with regards to black holes, right? And with regards to dark matter. So Sean is saying there isn't a lot of mass, therefore the centers of the galaxies don't get to a high enough rotational velocity to go ahead and have relative dilated mass. Let's use this term. And because there's no dilated mass, there's no signs of dark matter, and so the rotation curves are going to be weird as they are. Now, I didn't check the mass for this galaxy, but that's not what we're going to cover here. We're just going to kind of break down this logic and talk about one of the interesting things about astrophysics. And so, by this logic, essentially, he's saying low mass galaxies can't have black holes, can't have dark matter. So, this isn't really an astrophysics thing. I kind of misspoke. It's more of a cosmology thing. But to study the creation of the universe, we produce these sort of models of relative density, of dark matter, dark energy, matter, radiation, etc. And then we change said ratios over time to kind of change the density of the universe, and we see how things would change. And there are very, very complex simulations designed to simulate the sort of creation of the universe in and of itself, where they kind of start from the birth of the universe and through the Big Bang, or not exactly the Big Bang, a little bit afterwards, because it's really hard to know about the Big Bang. But essentially, within these models, they were finding, oh, if we include dark matter as something that exists, we get stuff that looks like nowadays. Because if we don't have dark matter, what we were finding was everything sort of separates really far out. And so essentially you would get a bunch of really not even lonely galaxies. It was really, there was an issue with things forming into galaxies and forming into stars because they weren't collapsing together quite as quickly. But if you had dark matter as sort of these heavier, lumpier particles, what you would get is these groupings of dark matter would attract mass, and said attract mass would slowly turn into the galaxy. And so the more massive galaxies seem to have the mass to essentially form into supermassive black holes. And so what you were seeing was the galaxies with a lot of mass and the galaxies with black holes should have a lot of dark matter in them. And so some galaxies that form with less dark matter might not be as massive. So that would explain what Sean is saying here. But again, I'm not an expert on these sort of simulations. This is like knowledge that I have acquired over time. So I might be misexplaining the vague observations, but that was kind of it. So that would explain what he's already covering, let alone, again, showing a picture of NGC 1277, which my picture is blocking, which is a thing with a black hole. And based on Sean's logic, the black hole wouldn't exist because it would be dilated mass. But if it was dilated mass, we'd have dark matter. Or what we would have what looks like dark matter. And it just all falls apart. This is just not well explained. Anyways, let's get that last little snippet in. We've only got like seconds left. I can't remember if this shuts off or not. Yeah, so that's the end of the video. Okay, well that's the video by Sean SO7 called, what was it called again? Dark matter is a dilated mass. What have we learned today? Well, we have learned that whatever this video is trying to tell us is very wrong, either in how it's trying to show it, and maybe there is an actual like concept here that I just couldn't find any sort of proof for online, or this is just really science garbage. And I kind of hope it isn't science garbage, but seeing the way the internet works nowadays, it's just terrible. So first and foremost, I'd like to say to Sean, I'm really sorry for ripping your video apart. There's none of these videos really have your face in them, but based on the comment you left, it seems to be something you're very passionate about. Don't stop being passionate about science and physics, but review how you're presenting information and review what sort of evidence you're putting forward. You have very, very cherry-picked and also incredibly misunderstood a lot of stuff. I don't blame you for misunderstanding it. This is relativity. It is hard. And, when you talk about things that deal with particles, which black holes do and dark matter does, you also need to kind of have a bit of a particle physics background to an extent to understand some other elements. And again, astrophysics background is also really helpful. So, don't feel bad. But, I hope from this video you may have learned a few things about how to present your ideas or concepts. And you know what? Talk to someone who's an expert. I am I have a physics background, and I am training to be a doctor. Uh, so I mean, I have knowledge, but I would say, more professionally, talk to a theorist at a university, or put some papers in your post. If you do another video, I would love to see it, and hopefully, see that it is considered better. For everyone else, I hope you've enjoyed this video. As disheartening as it was to kind of like rip apart some stuff that, again, I've kind of called it science slop, and this kind of was, again, I'm sorry, Sean, but it just sort of was. I really enjoyed myself, so I would like to do a bit more of this. If you liked this video concept, leave a comment down below, like, subscribe, tell me what you want to see more of, because I'll do this again. I'll I'll rip apart someone's project or video again, and maybe, even talk to experts who know more about the topics than I do. I'm only really very comfortable doing this about this video by Sean because, well, I know about dark matter. I've worked on 2 experiments relative to dark matter. I've been to so many talks. I have a background with astrophysics. So I've learned about black holes, and I've learned about relativity. So I had sort of the tools to talk about this. I can't really do the same thing if it came to like anti-evolution theorists. I could stand up and say, this is what I know, this is wrong, and poke enough holes, but I just can't do the justice that, someone with the biology background could, more justifiably. Anyways, if you're new here, hi, welcome to the Quantum Mic. Please leave a like and subscribe. I do a lot of physics content, as well as interviews with scientists and physicists and just experts in the scientific community. We're all about science here on this channel. And until next time, have a good one.